Hi folks, welcome to Unit 2 Lesson 3. So today we're going to start considering the derivatives of trigonometric functions. So we're going to focus on the derivative of sine x. And the reason why we're going to spend a lot of time on the derivative of sine x is because with the other rules that we've established so far and what we know about trigonometry, knowing the derivative of sine x will lead us to being able to determine the derivative of all the other trigonometric functions. All right, so your first task, now sine x is a completely different function from any of the other functions that we've worked with so far, so we need to start from scratch. So I want you to go back to the limit definition of the derivative. I want you to apply that to finding the derivative of sine x, and I want you to simplify it as far as you can. So make sure you check, look up any identities that you think might be useful. Okay, now we'll give you a bit of a hint. In simplifying that expression, I want you to see if you can determine two special limits that you're going to need to determine the value of in order to determine the derivative of sine x. Okay, so in simplifying, there's going to be some expressions in h for which, if you can determine those limits, you'll be able to determine the limit of sine x, derivative of sine x. Okay, so see as far as you go. You won't be able to go to the very end, but see how far you can get on the limit definition. Okay, so I'll now ask you to pause the video. All right, so we're back here. So hopefully you put this into the limit definition of the derivative. So the limit as h approaches 0. So the f at x plus h, so that's going to be sine of x plus h minus sine of x all over h. Okay, and as usual, this is an indeterminate form because it approaches 0 over 0. So that means we're going to try to do some algebra here. So hopefully you saw this first expression and realized that you could use the addition formula for sine x. So let's go ahead and see where that takes us. So that gives us sine of the first times cos of the second, okay, and then plus cos of the first times sine of the second, okay, and all that minus sine x and all over h, okay. So let's see where we can go from here. And one thing I noticed is that this first term and this last term both have a common factor of sine x. So let's do whatever algebra we have at our disposal. So if I remove a sine x, what I'm left with here I'm left with a cos h. And here this is going to be just minus 1. Okay, and then here I've got the cos x sine h all over h. Okay, now one thing I notice is that sine x and cos x are not dependent on h approaching 0. So right away I see that these two expressions within the limit behave like constants. All right, and what I could do is I could try to collect all the expressions that only have h in them. All right, now because there's no other common factors, I would have to do that by splitting up this limit. So let's see what happens here. So I got the limit as h approaches 0. Okay, so I'll keep this sine x. And again, I'll just distribute that division to both terms. And so here I can write cos h minus 1 all over h. Okay, so remember this is like sine x over 1, so that should be correct. And then here, same thing, I'll keep the cos x apart, and I'll write sine h over h. Okay, and this is where, again, sine x and cos x act as constants in this limit. So if I could determine whether these two limits exist, I could start to split up this expression using my limit properties. All right. Now the question is can these limits exist? Well, let's take a look. If I replace h by 0, okay, this is approaching cos of 0, which is 1, 1 minus 1. So numerator is approaching 0, denominator approaching 0. So this limit has a chance of existing. And same thing here. Sine of 0 is 0 over, of course, this is approaching 0. Again, another indeterminate form, so this might exist. So if I can figure out what these two limits are, and that they indeed exist as h approaches 0, then I will be able to determine the derivative of sine x. Okay? Unfortunately, this is not quite an easy task. So what I'm going to do now is I'm going to ask you to consider a graphical approach to determining the derivative of sine x. So here you'll notice that I give you the graph of sine x. Now I want you to try to determine the derivative, but you're going to use easy points. Okay? So I'm pretty sure you can see in this graph points where the slope of the tangent is very easy to determine. Okay? But I don't want you to just use those easy points. Use some other key points on the graph of sine x. Okay, so think about what the key points might be along the curve sine x, and I want you to actually take a ruler and actually draw tangent lines as best as you can, approximate the slopes of those tangent lines, and then plot those points on the graph to see if you can figure out what the derivative should look like, and see if that helps you figure out the value of these important limits. All right, so take some time to do that. All right, so we're back. So I'm going to do here. And so here, hopefully you notice that anywhere there's a peak here, looks like I've got a horizontal tangent there, horizontal tangent. So anywhere I've got those local maximums and minimums, I know that the derivative is going to be equal to 0. Okay, so of course we know this occurs at pi over 2. So at pi over 2 we have a 0. Okay, and then here this looks like 3 pi over 2. So we've got a whole bunch of zeros. Okay, so on and so forth. And now I'm going to try my best to draw a tangent. And when I look at the tangent line, so first of all, figure it might look at the x-intercepts of sine x, but there's actually there's a more important reason why I'm looking at those points. Because if I think of drawing, here I've got my slope of 0, and I see the slopes are getting bigger and bigger and bigger and bigger and bigger, and it looks as though at 0 is where I'm going to have the steepest slope. Because as I move beyond 0, I see the slopes are getting smaller, and so they're getting less and less steep as I get to the next maximum. Okay, so I'm going to try to draw as good a tangent as I can. Okay, so let's draw our tangent line here, and let's determine the slope. And I see here that it passes through 0, 0. As I move up by 1, the graph increases by 1. Notice that the uh, um, scales are different here. So it looks like the slope here is equal to 1. So that means at 0, the derivative has a value of 1. Now remember that this graph repeats itself. So when I go to this point here, I should also expect it to have a slope of the tangent of 1, okay? Because it repeats exactly this same shape. So there you go. It would also be 1 here. And let's test this out. Now we could sort of figure, there's kind of a symmetry there, but let's try to draw this as best as we can. Okay, and here it looks like as x goes up by 1, look at that. The y value goes down by 1. So it looks like the slope of this tangent is -1. So at this point, the derivative is -1. Okay, same thing here. The shape repeats. This point here, -1. And I hope that you recognize this function that seems to repeat still every 2 pi units, that has a maximum of 1, minimum of -1, but at 0 is equal to 1. Looks a lot like the cosine function. Now, I don't think we should be too shocked that the derivative of sine x would be another sinusoidal function, because if the shape of the function repeats itself, it means those slopes of tangents are going to repeat themselves every 2 pi units. But not only do they repeat themselves in a very nice way. So now, if we go back up to our limit definition, what does that tell us? I need the final answer to just be cos x. Okay? So if I were to split apart this limit, okay, let's say these limits do exist. I'm going to put the, the question mark here. What would I do? I would just split this up, limit of sine x times the limit of cos h minus 1 over h plus limit of cos x times the limit of sine h over h. That would mean that this limit here would have to be equal to 0 in order to get, because remember we said sine x just behaves like a constant. The limit of a constant, this would just be sine x. So that tells it that this limit must be equal to 0. And since this limit, again, is just the cos x acts like a constant, in order for this whole thing to be equal to only cos x, it means that the limit of sine h over h must be equal to 1. Okay? So if these are true and have these values, then this justifies that the derivative of sine x is indeed cos x. Okay? Now, we're actually going to see later on that you can determine, if we have time, that you can determine that this limit is equal to 0, okay, knowing that this limit is equal to 1, okay? So what I'm going to ask you to do for cos h minus 1 over h is put this function in Desmos and see if you can justify why it makes sense that this should be equal to 0. But this graph here is going to help me to compare sine h and h, okay? Because I essentially have these things written out, Let's say instead of x, this was h. This function here represents y equals sine h, exactly the function I have in the numerator there. And this line that I drew that passes through 0, 0 and has a slope of 1 would just be the function y equals h. Okay, if instead of x, I'm using h as my variable. And look near 0, because remember, I'm taking the limit as h approaches 0. So I'm only interested in this part of the graph as h approaches 0 from the left and right. And look at that. Look at the function sine h, and look at the function y equals h. Near 0, they're almost identical to each other. So what are we doing? As h approaches 0, I'm dividing two numbers that are closer and closer to each other. So it makes sense that the limit should actually be equal to 1. Okay? So while this is not a proof, it is a pretty good geometric justification that this limit should be equal to 1. I'll ask you to check Desmos for this limit here to see if you can make sense why that should be equal to 0. And that then confirms that the derivative of sine x is equal to cos x. All right? And I also want you to remember these two special limits. The limit as h approaches 0 of sine h over h is equal to 1, and the limit as h approaches 0 of cos h minus 1 over h is equal to 0. Okay? Now, by the way, we just happen to be working with h as our variable, but this limit is often written using the variable x. that if I'm taking the limit of sine x over x, as x approaches 0, that limit is equal to 1. And there's a lot of very nice properties that I may have a chance to talk about that come from the fact that near 0, these two functions are very similar to each other. All right? So what I want you to do now is I want you to take this derivative and see if you can use it to determine all the other trigonometric derivatives. Okay? Now, once you know the derivative of cos x, I think all the others should be fairly straightforward. Tan x, how can I write tan x using those two functions? So this one here is the one that actually might be the one that you gotta check your formula sheet, okay? And I'll give you a bit of a hint. You might want to look at your correlated angle identities in order to be able to write cos x as a sine function for which you should now be able to take the derivative. Okay, so take some time to get through as many of these as you can. All right, you can pause the video again now. All right, so we're back. Let's take a look at some of these derivatives here. So what I want to do in order to find this derivative is make use of the fact that I know the derivative of sine x. So how can I write cos x as a function of sine x? And hopefully you found that you have a couple of possibilities in your correlated angle identities, but one of the identities is that cos of x, okay, is the same as sine of pi over 2 minus x. Okay, this is one of the correlated identities, okay, where this cosine value is equal to this sine value. And now, lo and behold, we can use the chain rule to find this derivative, because this function here becomes my u. Okay, so what am I going to do is first I'm going to take the derivative of sine of u with respect to u. So I'm just using my chain rule here. I'm taking the derivative of the outside function, and then I'm going to multiply it by the derivative of my inside function. Okay, so now we know that the derivative of sine u, as we determined before, will just be cos u. But of course, instead of writing u, I'm just going to write cosine of pi over 2 minus x. Okay, and then here, well, this is a very easy derivative to take because pi over 2 is just a constant. So I'm just taking the derivative of negative x, which is negative 1. Okay? But if you look at your correlated angle identities, you would also see that cos of pi over 2 minus x is equal to sine x. Okay? And of course, don't forget that you have that negative in front. Okay? So not exactly quite as nice as the derivative of sine x, but we see again this relationship between sine x and cos x. The derivative of sine is cos, the derivative of cos is negative sine. Okay? So now that you have these two derivatives, you should be able to determine all the future ones. Okay? So take some time to work on a couple of them. I'll do maybe I'll do 2 of them when we come back, and then the rest you can find on your own. Okay, pause the video again. All right, so let's take a look at a couple of these other derivatives. So here, seems pretty clear that we should find the derivative of sine x over cos x. Okay, so here I'm going to use the quotient rule. So let's use the quotient rule. Derivative of the numerator is cos x times the denominator function, which is cos x. Okay, and then we've got minus the the numerator function times the derivative of the denominator function. The derivative of cos x we found earlier was negative sine x all over cos squared x, the square of the denominator. Okay, so let's do some simplification here. We have cos squared x. This is going to be plus sine squared x all over cos squared x. And lo and behold, look at the numerator. Sine squared plus cos squared is just equal to 1. So 1 over cos squared. But we don't usually write it in this format. What we usually write it as, since 1 over cos is equal to secant, this is secant squared x. Okay, so again, we're seeing that the derivative trigonometric function is itself another trigonometric function. Not surprising that one repeating function has a derivative that itself is going to be a repeating function. This time here, secant squared. Okay, so I'll just do cosecant, just do something a little different, and then you can finish off the other two yourselves. Okay, and once you get all 6 of them, see if you can come up with a way of finding tricks to remember them. Okay, so here again, I'm going to start by rewriting this as something I know, so 1 over sine x. Now, I could use the quotient rule on taking this derivative, but I certainly am not going to take the quotient rule. Instead, I'm going to write this as sine x to the negative 1 and use the chain rule. Okay, so this is my u. So now I'm going to write a little less than I did before, because the first thing I'm going to do is take the derivative of u to the negative 1. So that's going to be negative 1 u to the negative 2. And then I'm going to multiply that by the derivative of u with respect to x. And the derivative of sine x is cos x. And so now let's clean this up. So here I've got the negative. Cos x is going to stay in the numerator. And this u to the negative 2 is going to go into the denominator. But of course, what is u? It's just sine squared x. Okay? And this is a perfectly valid formula for the derivative of cosecant of x. Okay? But we actually write it a little differently. Okay? And you realize that this denominator has 2 factors of sine. So it's got like a 1 over sine, which is equal to cosecant. So what we're going to do is we're going to split up this fraction as negative cos x over sine x, and then we're going to separate out another 1 over sine x. All right? And then you realize, hey, wait a minute, cosine over sine is just equal to cotangent, and 1 over sine is just equal to cosecant. Okay? And in fact, it's usually written the other way around. Negative cosecant x cotangent x. Of course, it doesn't matter because this is commutative. But in the end, we see that the derivative of cosecant contains cosecant multiplied by cotangent. Okay? So I want you to find the other two on your own. Okay, later on if you have a chance during the period, or you can do it for homework, and see if you can find some nice connections between some of these derivatives that make them easier to remember. Okay, so the last thing you'll work on now is doing a couple of derivatives using all the rules that we found, and of course using now the derivative of sine, cosine, and here it looks like you're going to need tangent. Okay, and then we'll take them up, and that'll be the last thing we do in the video. Okay, so please pause the video and spend some time working on these 3. All right, so we're back. Let's check on these here. So I'm going to try to do as little writing as possible because I want to start kind of doing a lot of this stuff in my head. So let's do the first one. So f prime at x here will be, so I notice here I've got sine of another function, so I'll make that inside function my u. So I'm going to use the chain rule, and the first thing I'm going to do is take the derivative of sine u, which we know is cosine u. And of course, u is just x cubed minus 3x. And then I'm going to multiply that by the derivative of u with respect to x, which is nice and easy, just 3x squared minus 3. Okay? So again, I'm applying the chain rule in the exact same way as I did before, except instead of having this thing that's squared or to the 1/2 or to the 27, it just happens to be sine of this function. All right? So let's now move on to b. Okay, so clearly I'm going to have to use the quotient rule, okay? But I notice the denominator is just a composite function, so I'm going to have to use the chain rule here, and I see that this is also a composite function. Now, this is not something I would normally always do, but since it's something we're doing that's new, I'm going to maybe rewrite cos squared x in terms of what it's really representing. It represents cos x all squared. It might help us see what we have to take the derivative of. And here, again, maybe I'll still write 3x. Instead of square root of 3x, it's 3x to the 1/2. All right? So let's now apply our quotient rule. So I'm going to take the derivative of the numerator function. So this is like the derivative of u squared. Okay, the derivative of u squared is 2u. Okay, and I'm going to multiply that by the derivative of u with respect to x. So derivative of cosine is negative sine. Okay, and then of course don't forget to multiply that by the denominator function, root 3x. Okay, now minus that numerator function now, doesn't change. And now I have to multiply that by the derivative of the denominator function. So here, this is like having v to the 1/2. So the derivative of v to the 1/2 is 1/2 v to the negative 1/2. And then, of course, I have to multiply that by the derivative of v, which is just 3. And then all of this is going to be divided by root 3x squared. Okay, and obviously we can simplify this. Okay, but for now, I'm just going to leave it as is because I'm just interested in taking the derivative and not worrying about simplifying it right now. Okay, now C is a pretty nice one because I see that I've got a function of a function of a function of a function. Okay, I think I'm going to have to use the the chain rule a few times here. So the first thing I might do is rewrite this. Okay, actually no, let's not rewrite it. Let's just leave it as is. Now I actually see a little trick I could use to simplify my life a little, but I'm just going to sort of take each of these functions separately. So this whole thing inside the cube root is just my inside function, so I'll call that u. So I have to take the derivative of u to the 1/3, because cube root is the same thing as 1/3. So that's going to be, okay, so f prime at x. I'm going to have to leave myself a lot of room here, I think. This is going to be quite long. It's going to be 1/3 u, which is 10 to the 4th of 2x squared minus x minus 7, all to the negative 2/3. Okay, so now we can forget about the cube root and now focus on just taking the derivative of this function here. But remember what tan to the 4th of this thing represents. It represents the tangent all to the power 4. So my next function is like v to the power 4. So that's going to be 4 times v. I should put brackets here, which is tan of 2x squared minus x minus 7 all to the power 3. Okay, so 4v cubed. And now I have to multiply it by the derivative of that inside function, which is going to be the tangent of 2x squared minus x minus 7. But again, I have to use the chain rule again because it's like taking the tangent of w. What is the derivative of the tangent of w? Well, it's just secant squared of W. Okay? And then finally, we get to the last derivative we have to take. That last inside function is the derivative of 2x squared minus x minus 7, which is just 4x minus 1. Okay, so here we had to use, there were 4 links in the chain because we had the exponent 1/3, we had the exponent 4, we had the tangent, and finally we had the innermost function, the 2x squared minus x minus 7. But if you take each component separately, they're all easy functions to take the derivative of. Okay, you have to just not get thrown out by all the writing. Okay, now you might want to think as to how I could have made my life a little simpler in this question here. Okay, or you might even want to think about how I can determine this limit knowing that the limit of sine h over h approaches 1 as h approaches 0. Okay, and I will give you a little hint. If you do try to do this one, you have to use an algebraic trick, which we have used in other contexts. Okay, that's it for this one.